Hello, welcome to the technical session Profiling Heterogeneous Computing Performance with Intel VTune Profiler. My name is Vladimir Tsymbal. I am a technical consulting engineer at Intel Architecture, Graphics and Software Group. During this session, we will quickly go through the Intel GPU microarchitecture, the development environment for executing the GPU applications, performance metrics, and we'll discuss how VTune can analyze the applications for performance which are offloaded to GPU. Also, we'll take a look at the applications which are written on SYCL DPC++ application, OpenCL or OpenMP offload model. Then we will observe some in-kernel analysis, memory stalls in GPU microarchitecture, GPU instructions, and memory and basic block latency analysis in the tool. And finally, we will observe some platform analysis on the system. A quick observation on Intel GPUs which are available on the market so far. First of all, it's embedded Gen 9 graphics, which is going along with the Coffee Lake processor and later. It has up to 48 execution units, each has up to 7 threads, and each EU can execute up to 2 CMD4 instructions, either 32-bit floating point or integer data. The Iris Xe Max is a discrete GPU which is scaling up number of execution units, also doing 7 threads simultaneously. It has its own RAM memory, and of course it's connected through the PCIe card to the main system. Software development for GPU is supported by several frameworks available from Intel or other partners. First of all, it's high-level languages based on OpenCL technology via Intel Media SDK, direct programming with SYCL or data parallel C++, OpenMP offload model, and of course performance libraries which have been available from Intel for many years. All those supported with the set of Intel compilers which are available either for classic programming by C, C++ for CPU, and programming on high-level languages for GPU, for GPUs, CPUs, and FPGAs. The software runtime has a quite complicated architecture, and on the example of DPC++ application, you might see that it has a high-level conversion of DPC++ application or SYCL application to the SPIR-V format. Then it goes to the runtime based on SYCL API, and inside there are plugins for binary management, which can split execution either to OpenCL based runtime or level 0 based runtime. Level 0 is the Intel extension to the runtimes, providing more capabilities to the existing OpenCL runtime. Then finally, it ends up in the drivers for devices, concrete devices, either GPU, CPU, or FPGA, or other accelerators. And one thing to remember that performance tools, performance analysis tools, they are collecting metrics and information pretty from each level of this runtime architecture. That gives us a lot of opportunities for performance analysis. Let's start with VTune offload analysis. This is actually the high-level analysis type, which helps to focus on both CPU and GPU execution to correlate the activity between those and find out what was the interaction between CPUs and GPUs, and identify whether the application was CPU bound or GPU bound. That helps to find the best candidates for further analysis based on each tasks, find out whether the execution of kernels were effective or not, were the data transfers the main bottleneck, or it was a pure execution performance problems. Once offload analysis is completed, VTune is presenting us some measured metrics and recommendations on what might be wrong with the execution of our tasks. In this case, we've been working with very bad application, and VTune is noticing that most of the time execution units, they were stalled or idling, and that's why we need to take a closer look into the particular kernels or tasks being executed. Also, it noticed that the time of execution of the task were extremely small comparing to the memory transfer time. And you probably need to take a look into the data transfers during the execution. Which exactly compute tasks were involved, you can find out in the table below, which is named as the hottest GPU compute tasks. You might notice that most of the time it took to complete the compute task, it was spent on something else rather than execution. So that the percentage of execution time for the task was extremely small. That means we need to take a closer look to the structure of the task and find out whether the data transfer or something else was the reason for such a small percentage of real execution of the task. Switching to the graphics tabs, it gives us much more detailed representation of the all the executing tasks which have been running during the analysis. On the top, there is a list of the compute tasks, and on the bottom, there is a timeline view, which is presenting both CPU and GPU execution in the time. Let's look at the list of the computing tasks. First of all, we might notice that there's one single task, which is matrix multiply 1, is the only candidate to analysis, as it takes most of the time of execution. Although its execution time, as it was presented in the summary, is extremely smaller than the time that it was spent for host to device and device to host data transfer. So you might also notice that the amount of data being transferred between CPU and GPU is quite big, and then you might need to analyze whether all this data is needed to be transferred between CPU and GPU. And finally, you also might need to understand if the amount of instances of the kernel being executed is corresponding to what you're expecting. Probably this kernel was is being called too many times, and this might be the reason of such a overhead for execution. The timeline view on the bottom gives us much more detailed picture on how the compute tasks are being created. Notice that there is a CPU and GPU side, and the particular task for executing on GPU, they were created on the CPU side. So you might observe how the tasks are being created and put into the queue. So we might want to take a zoomed or closer look onto each task to understand the structure and how it's being executed. So if we zoom in into the individual task, then we can observe the parts that the task consists of. So this is the level 0 API, which is like allocating a device and then the copying the data to the GPU. So as expected, the data transfer takes most of the time for the task execution completion. So the execution itself takes the extremely small amount of time. So the rest of the task execution is just bringing the data back to the host. So with that, we can analyze and conclude that the each task is executing extremely small amount of job, and most of the time it takes to transfer data from host to the GPU. And since there are several thousands of instances of this of such tasks, so we might need to reconsider the granularity of task creation for offloading to GPU. Let's observe the high-level languages supported by VTune analysis. First, we've been already analyzing the application example written on SYCL or DPC++. And according to the nature of the one-source approach, the host code and accelerated device code can reside in the same source file. So VTune will be attributing the characteristics of execution kernel against the device code, and the rest is attributed in the CPU metrics against the host code. In OpenCL applications, kernel source code usually is separated from the host code. Anyway, VTune will be presenting the tasks as a OpenCL task separately analyzed as if it was done in the SYCL DPC++ applications. Of course, the rest of the host code will be analyzed on CPU if it's relevant for the current analysis. It's just for your reference that there is an OpenPo offload model as well, which can help to offload some execution to GPU, and it can be analyzed as a kernel in VTune, like it's done with OpenCL or SYCL kernels. In addition, it can be analyzed with the classical VTune analysis like HPC characterization. Okay, once you defined you need to go further and analyze individual computing tasks, you need to select the GPU compute media hotspot analysis in VTune and then find out which predefined analysis type you want to use for further analysis. So it gives a basic information of each individual compute tasks like sizes, global and local size, the timing information about the execution of the kernel, the CMD width instruction characteristics, and the data transfer sizes. But what about the efficiency of execution of compute tasks on the execution units? One of the main metrics of efficiency is how much or what is the portion of the task being executed actively on EU or being stalled or idle. Here in the grid table, you will have the metrics highlighted against each compute task, and so you can find out how much it is actually stalled during execution. The execution stalls usually happening due to delays of fetching data from some of the units of memory, either close caches or remote caches or remote memory and so on. So to help to find out where the stalls might be and what was the reason for the stalls, we have a memory hierarchy diagram which is presenting the computing unit, slices and computing units, and the data transfer rates like bandwidth or amount of megabytes or gigabytes transferred between the data units and execution units and so on. So if you observe some limitations in bandwidth, for example, level 3 cache bandwidth or memory bandwidth, and so on. So it will be highlighted as a pink against the computing task on the grid table. So there are several metrics which are reflecting the bandwidth between the execution unit and different memory units. And based on where these limits might happen, you can define and you can decide on how to better and more efficiently organize the memory access and how much data needs to be transferred between the execution unit and this or that memory source. Another reason for inefficiency of executing of computing tasks might be latency of instructions being used inside the function call and or implementation of executing kernel. So it's important to understand the decomposition between instructions which are being generated by compiler and which are being used inside the execution kernel. In addition, the successfully vectorized instructions is one of the key goals for good performing applications. So you might also want to understand if CMD instructions were generated or not for the particular execution kernel. So a separate GPU instruction count analysis is available in VTune for that purpose, where you can have the instruction decomposition against each computing task, and under the computing task, the distribution of the instructions can be seen against each function that presented inside the computing task. So in this case, we have the matrix multiplied to function call and their set of instructions being used to generate this call. So it's more or less evenly distributed, and you can find out what does the portion of instructions being spent in either calculating some math functions or sending data or just for control flow. And when you switch to the source view by double-clicking on any function name, you will get into the source view and the instruction decomposition against each source line, which helps you to figure out what was the instruction sets generated for each implementation or each of the source line for your kernel. In this case, it's more or less simple kernel, so most of the instructions were executed against the main loop inside, but for more complicated kernels, you might find it very useful and quickly identify in a graphical way which exactly part of kernel, which loops are taking most of the instructions and which types of instructions are generated for that particular loop. When you want to understand which exactly portion in terms of CPU cycles of time and which function took most of the time inside your computing task, you'd be using basic block latency analysis type in VTune. And like in this picture, it's providing the distribution of estimated GPU cycles against each function call inside the kernel. This analysis type basic block means that the latency in CPU cycles is defined against the blocks where there is no jump instructions. It's something like a loop or full function without any jumps and so on. So against the source line, you can have the same GPU cycles distribution characteristics shown in the source view. So with the more or less acceptable precision, you will define which loops are contributing in the execution time of the kernel and how much in percentage of execution this or that loop might take from the whole execution time of the kernel. As we already discussed earlier, the most probable reason for delaying of execution instructions in kernel would be accessing data from some units of memory. That creates a latency. So for more fine-grained memory latency analysis, you'd be using the VTune memory latency profile, and you will get the average latency in CPU cycles against source lines. But if you switch on the assembly pane, then you'll get the corresponding disassembly view, which corresponds to the selected source line. And then the average latency metric would be given against each instruction which is related to memory access. And finally, after we are making some efforts to optimizing execution of kernels, data transfers, and other aspects of software, we might want to take a look back to the whole platform execution and observe how the offload application is being executed on both CPU and GPU. So the platform analysis tab is intended to show overall picture of the application execution in the system, showing the tasks, their timing, and creating queues and so on, the busyness of the GPU execution units and creating compute tasks and so on, and the traffic on the different interfaces like DRAM controller and PCI, where you can find out either average numbers for the execution or the numbers or limits for the bandwidth during the execution time. So it gives more or less the comprehensive picture of how the workload is balanced on the system and if there are any particular bottlenecks in terms of I/O interfaces or compute units in the system during the execution of the whole application. In the end of the presentation, I would like to mention that, of course, we skipped all these details regarding how to launch this or that analysis, how to select a particular profile in VTune, because it's just the mechanics how to use the tool. But if you're new to the VTune and other Intel tools, just feel free to find the product page where there will be found a lot of overviews, FAQs, training materials, cookbooks, user guides that are extremely helpful for those who are just beginning to use Intel tools. Of course, we have a support forum where Intel engineers would help you to solve some problems that you might face with. And of course, there is a service center for primary support of our customers. And there are pages where you can stay tuned to all the new features that are coming inside our tools. So feel free to visit the product pages and find out the sources of support. This concludes the presentation. I really appreciate your time. Thanks a lot for your attention and have a nice day.